we have read the permutations of a set, and what do we mean that R permutation of a set of n elements. Now, this lecture will read the combinations of set. As already I have defined that normally that permutation combination they are concerned about the counting of ordered or unordered arrangements. So, this is the combination is concerned when we counting techniques for unordered arrangement. So, it is concerned for unordered arrangement. Now, we first define that what do we mean by these combinations of a set. So, let R be a non-negative integer. Now, by an R combination of a set of n elements, what we understand is this is an unordered selection of R of the objects or elements of a set of n elements or n objects. A set of n elements. Now, it differs from permutation is that unordered selection. Okay. So, I can write that from the concept of set, the definition of set. So, I can write that R combination of, since it is unordered, so I can write the R combination of S having n elements is a subset of S where S has of subset of S having R elements and this S has, so R combination of S has where S has n number of S has n elements or S is an n element set. S has n elements. So, this is since order is not concerned, order is irrelevant. So, I can tell simply this is a R element subset from the set S of n elements. So, if one simple example if I take, say S has 4 elements, okay. S has 4 elements A, B, C, D. Then what will be the 3 combinations? I can write the 3 combinations. That means, I have to take the subsets having 3 elements from these 4 elements set S. So, 3 combination of S, these are equal to this. I can tell this is ABC, I can write ABD, then it can be BCD, then it can be ACD. So, these are the 4, these are the 3 combinations. So, this is the difference from the permutation. So, normally we denote the combination, these are combination of n elements, we denote as NCR, or sometimes that n choose R, then sometimes we write in this way also. So, according to their definition, I can write that NCR equal to 0 if R greater than n, because not possible that among that n element set I can choose a R combination subset of subset having R elements and R greater than n. So, it is not possible. So, this is equal to 0, I do not have any such subsets. Then I can write 0 CR is actually 0, that if R greater than 0. I can put NC 0 equal to 1. If I think only the way we have defined, as if only the empty set I am taking subset, then NC 1 only one element set, since I have n elements. So, this is n, then NC n, that is the set only. So, this is again 1. Okay. So, this is according to my definition, the way we have defined to the definition of combination or R combination of n elements. Okay. Now, we try to find out the formula and we write a theorem. Write for 0 less than equal to R less than equal to n, then PNR, that n permutation of R permutation of n elements, PNR is R factorial into NCR. So, I can write the NCR is PNR divided by R factorial. Already we know that PNR is n factorial divided by n minus R factorial. So, I can write. So, this is my, we know these are my R combination of n elements. Now, how to prove, how we can give a proof. See, now we know the R permutation of n elements, and that is a ordered arrangement or ordered selection. So, we start with the ordered selection and see how we can make the ordered selection. So, let S be a n element set. Now, each permutation of S arises exactly one way. What is this? I choose R elements from a set for a set S, and since it is a ordered arrangement, I am considering permutation. So, I can write arrange the chosen R elements in some order. So, from the definition of permutation, I can write this thing. Now, we see that how we can write. So, if we see the first one, choose R elements from a set S. So, this is nothing but my definition of R combination of n elements. So, the first one, that choose R elements from a set S, having choose R elements for set S having n elements, is nothing but my NCR. This is nothing but my n chooser, and the second one, that arrange. So, the arrangement is ordered arrangement in some order. So, that I can write, that is my permutation. So, second one I wrote that ordered arrangement. So, according to the definition, I write that is nothing but my PNR. Now, here this PNR is R factorial, or PRR is R, PNR. If it is R element, it is. So, if it is PNR, if it is PRR, then means from. So, I can write this is my R factorial. Now, we know that PNR, we know that already we have got, this is n factorial by n minus r factorial. So, I can write that my NCR is PNR by R factorial. See, I can I have written, yes, this NCR is I can write that this is PNR by R factorial, or actually I can I should write this thing first. PNR is R factorial into NCR, because two steps I have written: choose R elements for a set S and arrange the chosen R elements. Arrange the chosen R elements means this is PRR. Okay. Ordered arrangement is PNR. So, R for R element, it is PRR, and that is R factorial. So, PNR is R factorial into NCR. So, NCR is PNR by R factorial, and PNR already we have got n factorial by n minus R factorial. So, this is our expression for the combination, R combination of a set of n elements. So, I got this thing. Now, we see some problems with this combination. First, we see some simple example, how we can use this formula of NCR. Okay. Say I have 25 points are chosen in a plane. So that no three of them among these 25 points are collinear. Then the counting problem is that how many straight lines we can draw, or do they determine with these 25 points. Then also we can find that how many triangles we can form. With these 25 points having this property that no three points are collinear. So, first thing is this is a pure counting problems and there is no ordering. So, unordered arrangements. So, I can give the solution. The first one, that straight lines. So, no three of them are collinear. So, with each 2 points we can draw a straight line. Now, I have 25 points. So, I have to, the problem I can think that 2 combination of 25 elements. So, this is 25 C2 equal to 25 factorial divided by 2 factorial into 25 minus 2 n minus r, and this becomes 25 factorial divided by 2 factorial into 23 factorial, this is equal to 25 into 24 into 23 factorial divided by 2 factorial is 2 into 1 2 and this is 23 factorial. So, this becomes 25 into 12 is 300. Now, how many triangles we can give? Since no 3 points are collinear, so with any 3 points we can draw a triangle. So, I have 25 points and we have to choose 3 points, any 3 points. So, the total number of combinations are simply, that means any 3 points or I can write with any 3 points one triangle can be drawn. So, this is simply 25 C3 again the similar way. So, this becomes 25 into 8 into 23 is 4600. So, we can see that how directly we can apply the formula of the combinations. Now, we can the theorem we got that NCR is n factorial by r factorial into n minus r factorial. So, I can write a corollary that if I write NC n minus r, that means I am giving r equal to n minus r, then I can write n factorial to n minus r factorial and n minus r is n minus r factorial. This becomes n factorial minus n minus r factorial and this becomes r factorial. So, this is equal to NCR. So, the corollary is that NCR is NC n minus r. So, I can give this thing also. Now, we take another example. Take some 8 letter, say how many 8 letter words can be constructed using 26 letters our alphabet set. If each word contains either three or 4 or 5 vowels. So, the problem is that I have to frame a 8 letter word, and from the 26 alphabets, that A to Z, and the restriction or the property satisfying the property. See, we can remember that in the definition of, when we started with the definition of permutation and combinations, that some ordered or unordered arrangement satisfying some property. So, here it is contains either, each word contains either 3, 4 or 5 vowels. Okay. So, first I consider the 3 vowel case. So, okay, the case 1, I am taking that word contains the words containing 3 vowels. Now, since there are 3 vowels, so in this case there will be 3 vowels and 5 consonants. So, in the 8 letter word, so I can in 8 letter word, three vowels can be chosen. How many ways? 3 vowels can be chosen. Say HC3, that means, say if I take in this way, say as if this is a 8 letter word, 4, 5, 6, 7, 8. So, these 3 vowels that I can put in 8C3 different ways. So, I can choose here. So, 3 vowels can be, the vowel can be here, it can be here, it can be here. So, 3 vowels I can put. This is the way. Now, since there is no restriction that of repetition, since there is no restriction about that how many times I can choose, how many times about the occurrences of vowels. So, there are 5 vowels. So, I can keep 5 to the power 3, because I have 3 vowels and there are 5 different vowels. So, I can put this ways. Then the remaining 5 places, so we have 21 consonants, and there are 5 places for them. Since 3 places already vowels are there and there are 5 places for them, and that we can put I have 21 to the power 5. These many ways I can put the consonants. Okay. So, the case 1, that what we are telling, that for how many ways that, or we can 3 vowels, or the number of words having 3 vowels, I can write number of 8 letter words with 3 vowels. This is equal to, I got, this is the 8C3 ways I can put the 3 vowels. Then since there are 5 vowels and 3 positions, so 5 to the power 3. So, I can write that this number equal to 8C3, then 5 to the power 3 into 21 consonants to the power 5 places. Now, if we just extend the idea that when number of 8 letter words with 4 vowels. So, I can write, so 8, these will be 8C4, since now I can choose 4 vowels from 8 letters, 8C4 positions. There are 5 vowels, 4 places, 5 to the power 4, 21 consonants, rest of the 4 places, because I have 8 places. So, this is my rest of the 4 places. Now, I have number of 8 letter words with 5 vowels is 8C5, the similar way, then it is 5 to the power 5, and this becomes 21 to the power 3. So, now I have that addition principle, because my question was that either 3 or 4 or 5. So, the total number of words having 3 or 4 or 5 vowels, this is equal to the, I have to add, because with 3 vowels, 8C3 into 5 to the power 3 into 21 to the power 5 plus 8C4 into 5 to the power 4 into 21 to the power 4 plus 8C5 into 5 to the power 5 into 21 to the power 3. So, this is my answer. So, for unordered arrangement for accounting problems, we can use the combination like that. Now, sometimes we require this what will be the total number of combinations. That means, if I consider the from a set of n elements, set, then the way we choose the elements, say I can start with that as if I start that NC0, I have chosen 0 elements, I can choose 1 element, I can choose 2 elements, I can choose 3 elements. In that way I can choose up to n elements. That means, this sum tells about the total number of elements that we can total count that we can choose the elements from a n element set. I can choose 1, I can choose 2 at a time or 3, and these will be my is 2 to the power n. Sometimes we write this thing as a theorem also. We can write this thing as also a theorem, and we can prove this thing. If from the definition only, actually we can prove this thing, that this is my the total number of ways we can choose elements from a set S with n elements, and this is my, say actually this is my left hand side tells that thing. I can choose 1, 2, 3 like that. What my right hand side tells? Very simple way I can think, if we have n elements, and as if I am making 2 partition. So, whether these n elements, and I will be taking some combination or not. Now, that means, if it goes to this combination, I am giving 1. If it does not go, then I am putting 0. That means, if it goes to combination 1, if it does not go, I can take it is 0. So, that means, if it is n, this is nothing but the all possible ways I can write the thing as 0 0 like this. If I have 3, I can tell that it is 0 1 0 0, or I can write that all possible way. If it is only n equal to 3, I can write 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So, these are the way. That means, these I have not chosen any combination, here only this element goes to combination, here this element goes to combination, here these. So, these are all possible way that we can take the combination. That means, whether, and here see we have covered when n equal to 3, we have actually covered all the combinations here, and all of we know this is just, if we can think in this way, this is a binary representation. So, it is a as if the n variable n bit binary representation. So, I can write this is 2 to the power 3. So, when this will be some for n elements, I can think we know that this count is 2 to the power n. So, if the RHS we can think that as if these n elements and whether I take the combination or not, that means if it is goes to that combination partition, just we are thinking like that, we are defining in this way, then this RHS is nothing but 2 to the power n, RHS is nothing but 2 to the power n, and the LHS is actually it gives a total number of ways we can choose elements from a set with n elements, and this is definition wise, according to the definition the LHS and RHS are same. So, I can put this thing. So, I can treat this thing as my proof. Sometimes we take this as this property as if this as a theorem and then proof. We use this relation for solving some of the combination problem.